Welcome all to today's ASRG World webinar. We have the 6th of May 2021 and we are streaming from Stuttgart in Germany. Thank you for being with us. My name is Sven Schran and I am coordinating with ASRG the European locations. The Automotive Security Research Group is now nearly 4 years old and we are a non-profit organization. Provides a platform for the automotive security industry, as well as related academics or organizations to share knowledge, build powerful networks, and valuable collaborations. This community is for you, and it's based on volunteer support. If you want to know more details about ASRG, please check out our webpage at www.asrg.io. Send us your questions via email to hello@asrg.io or follow the links in the description below of this video. Maybe you have an idea for a nice project and look for partners to realize it. You would like to start your own location. You have an idea about a service ASRG could provide, or you know a great organization which could partner with ASRG. We are open to hear each idea you have in mind and would like to discuss how ASRG can support. Don't hesitate and get in touch with us. So, this is enough from my side today, and I don't want to keep you tortured anymore because I'm very sure you are waiting very curious for our main presentation. Like every time, in case you have questions during the presentation, please write it in the chat window. After the session, we will have some more minutes for questions and answers. And now it's my pleasure to welcome Mathias Weber, Managing Director and founder of SecOps Solutions. Today, he will bring to us the topic Vehicle Key Lifecycle Management. And now I would like to hand over to Mathias. The virtual stage is yours.
Thank you, Sven, and thank you all very much for joining my talk today about vehicle key management systems. So when Sven approached me a few weeks ago and asked me if I could tell a little bit about my experience when it comes to cybersecurity, and especially vehicle key management systems, I was trying to come up with a way of how I could start with this topic because it's kind of complex. And this event is targeting a more broad audience, as I understood. So I would like to do the following. I will start with a short introduction of myself, so you will see who I am and what I did in my past. I will then go on to chapter 2, which is basically a small overview of product cybersecurity as a whole. We will talk a little bit about cyber risks and threat scenarios, and I will draw a very, very simplified example attack path. Please bear with me. I'm far from being an expert on threat assessment. And going from there, I want to show why we need cybersecurity controls in vehicles and in control units. And going from there, I will show why we need vehicle key managements to enable those controls. When we are there in chapter 4, I will dive in a little bit into what a vehicle key management is, how you can build it up, which components you probably need, and the challenges we saw so far when doing vehicle key management systems at our customer sites. So let's start right away. So my name is Mathias. I'm an electrical engineer. I studied electrical engineering and technical information system in Munich. And I started doing mainly information security work and software engineering back in 2010 when I was finished with my studies. I did this for several years until around 2017. When we had the first chance of building up a key lifecycle management system at a tier 1 supplier site. And this was kind of successful, I would say, in a way that we saw it exploding when it comes to stuff we needed to do and support we needed to give to our clients. And going from there, we said this is nothing we want to do exclusively for one customer. So we decided to found our own company. When I say we, I mean I'm talking about my colleague Marcus and myself. So this was the point where SecOps was founded, especially for the goal of setting up and operating vehicle key lifecycle management systems for automotive companies. Going over to product cybersecurity as a whole, it's hard for me to find the right entry point for this. So one of the common things all of you probably heard by now is that there is a few regulations and standards coming up. So this is a small overview of how we see it right now. So there is the regulation 155 and 156, which are both describing cybersecurity management and software update management, which were basically released in January this year, and already are in force for the UNECE WP29, and they are actually already in force for the national registrations of new vehicle types in Japan. And going on to July 20 or somewhere in 2022, we will see the same thing for the EU. I mean, regulation in force for all vehicle types, and Japan will basically go over to setting this regulation in force for all vehicle registration. So to not leave everybody alone with this, there was also at the same time a new standard drafted up, which is the ISO SAE 21434, which basically tells you how to do CSMS and software update management system as a whole. They are not tightly copied from a legal point of view, but it's expected that if you are compliant to 21434, that you will also be have an easier way to get your regulations for 155 and 56 done. This is valid for basically all vehicle types for software update management system and for all vehicle types M and N, so trucks and buses and cars for the cybersecurity management system. So the question which comes up when talking about those regulations is basically if you start in this field of work is, so why do we need cybersecurity in the automotive? Don't we have information security? Isn't this enough? I mean, this is basically an old thing. We are not inventing something really new here. But one thing changed, and this is how cars look like today. And more and more in the future. So this is a very, very simplified modern car model architecture, and you see something which is a huge driver for product cybersecurity, which is the connectivity. We have a bunch of functions which are connected to, let's say, the internet or the ecosystem around the car or other cars or the driver or the mobile system of the driver. In this case, I'm using this simplified car model architecture for as an example, a tech path I'll show you in a second. I just said, okay, there is an infotainment ECU, which is an human machine interface, or at least some control unit connecting to the internet or through Wi-Fi to the mobile system of the driver. It is probably connected through the very complex in-vehicle field buses through CAN, Ethernet, FlexRay, whatever you have there, to, let's say, lower level control units or functions, which is, for example, the engine ECU. And at the other end of this line, you basically have a connection to the physics around the car. So for the engine ECU, you probably have something by wire, like steering the wheels or the engine. So of course you have a lot more of those functions and those control units, but for a simplified attack path, this is probably enough. So when I say we don't invent new stuff, why is there a need for product cybersecurity at all? And yeah, so with the better internet connectivity or connectivity, generally speaking, you have probably remote access to the car, which wasn't there before. So before the car was connected, it was basically only an information security issue you had when producing this software or hardware unit. When it comes to connectivity, you basically enable the car to be accessed from the outside, which is always a threat in itself. You have customer data in your infotainment ECU. This is something which we see getting very big in the future. So we are in the middle of a transition from the old automotive industry being supplier of a mobility platform to something we call mobility as a service. So this is driven mainly by more and more data of the driver of something around the car or something else. So you have a lot of customer data in the car, which could potentially be stolen, which is a risk as well. You have more software in the car than in the past, which enables more attack scenarios. You also have more and more internal networks, which are very integrated. So an internal attack traversal is not only thinkable but very easy to do. Besides the loss of operation, which is the most basic threat you might have, you also have possibly the theft of intellectual property, and so on and so forth. So at the end, you even have a safety case when it comes to the physics. So overall, we have a bunch of threat scenarios we might not had in the past because there wasn't as much software in the car, not as many data in the car. The car was not so connected. So we could theoretically say it's fine, but now and in the future, it's getting more and more important to address those threats. So when you do cybersecurity management for a product like the car, it's one of the main things you do is a threat assessment and risk analysis before you talk about cybersecurity controls as a mitigation for those risks, and to show you what kind of attacks we might see in the car. This is far from being complete or anything. So this is only to show you guys what might happen or what could happen, and based on that, what we could do to prevent this. So with a better connected car, it's theoretically possible to gain access to the car network from the outside, and this is nothing we are thinking up. It's already has happened several times now for different vendors. Once inside infotainment ECU, you basically create a foothold, which is very similar to what you would do as an attacker in web attacks or other data center based attack scenarios. Since you have a lot of open source software or with AUTOSAR adaptive stacks, Linux components in the ECUs, it's kind of it's kind of good to do. Based on the foothold, you might want to do something like you might want to flash your own software over the Ethernet into another ECU to make it do stuff it wasn't intended to do, to reach a target you as a potential attacker would try to reach. So, for example, what your malicious software could do in an engine ECU would be to send some messages over CAN and to some actors, and basically do something like a full break on the highway or whatever. I mean, there are endless possibilities of attacks with different impacts on safety, operational privacy, and other impact scenarios. So going from this example attack path, one might ask, how can we address this now? I mean, if this is so easy, can't we do something to prevent this? And the answer is, of course, yes. And we might want to do something like, okay, to prohibit to gain access to the car network, you could do something like a debug access protection for onboard diagnosis. You might want to add reverse engineering protection in your infotainment ECU, which is basically encryption of the software, which makes it harder for an attacker to get information about how the ECU is working or how the software is working. You probably want to add secure boot for the engine ECU or other ECUs, which prevents the flashing of malicious software. You could also, and this is one of the main things we saw at the beginning, secure your onboard communication, because this will disrupt basically all the or most of the potential attacks on the network. Is secure. You might want to do secure onboard communication. I don't want to go into detail a lot for all those controls, but I will show in the end what the common denominator for all of those controls is. In the end, what you can achieve is probably, hopefully, better security in a way that the risk you addressed or an attacker might address is harder to achieve or even impossible to achieve. So some of the more common cybersecurity controls we see in the at our customer sites projects currently. I have listed some of those here. So we already saw the secure software update, which is basically a protection against arbitrary malicious code execution in the product with an update mechanism. So the software which needs to be updated needs to be signed by a trusted source. So the bootloader or the updating mechanism on the chip will check if the signature is fine. And only if this is the case, then it will accept this package and update the software. You might want to add diagnostic hardening for certain attack scenarios, which is basically protection of the unified diagnostic service against unauthenticated access. So what we see here is normally a seed key mechanism in place for any requester to go through before he is allowed to access certain functions on the UDS. Then we have debug protection, which is basically a lockdown of the JTAG access, the JTAG interface with a password or something else. We have secure boot, which is basically a signature on any application software after the first stage bootloader or after the bootloader, which then checks if the signature is fine. And only if that is the case, then it will allow the boot up of the control unit. Otherwise, it will prohibit the malicious code to be run. Secure onboard communication is basically the same thing. You sign your messages on the bus with a cryptographic mechanism. And all the accepting the receiving units will be able to tell if this data transmission unit was coming from a trusted source. Reverse engineering protection is, we already had that, is basically a data rest encryption of application files. So all of those controls are basically just higher level functions using cryptography, right? So we talked about signing and encryption and passwords, and all of that is basically only asymmetric or symmetric cryptography using distributed trust. So for all of those controls, you need keys, you need certificates or passwords or whatever, and those need to be present in the unit, and you need to protect them in the unit, and they need to come from a trusted source. Otherwise, you would probably only enable an attacker to switch out a key with his own key, and then you haven't won anything. So what we saw so far is mostly symmetric cryptography because it's supported by the high volume chips. So secure hardware extension is one of the main standards here, but we have also AutoSAR crypto stack supported functionality when it comes to asymmetric cryptography. But in the end, it boils down to what it always boils down to in cryptography, and this is a key distribution problem. So when I say distributed trust, I mean, how are we able to distribute the keys and the certificates needed for this control to work in a way that it is secure and protected, and nobody unintended has access to this key. And this is basically where key lifecycle management comes into place. When you look up key lifecycle management generically, you will find very fast a NIST standard, which is the 800-57. And that one defines how you do key distribution and key lifecycle, generically speaking, not only for cars or vehicles, but also for PKI systems, or basically for anything. So I put a screenshot of the executive summary of the NIST standard here. I also linked the standard here in this slide deck. So if you're interested in any details, please have a look. It's a good read. As an executive summary, we basically want to protect and manage cryptographic keys. So one of the main things stated here is the secure generation, storage, distribution, use, and destruction of cryptographic keys. And this is basically what the vehicle key management tries to do. It wants to create cryptographic material that can be symmetric, asymmetric keys. It can be password, certificate. It doesn't really matter. We also have very blob-wise data in our key management systems, like I don't know, user control block data, or even complete files. It doesn't really matter. Anytime you have something which is sensitive and basically secret, you need to protect it in a way that only the participants in let's say the communication, or the participants of in the control are able to access this cryptographic material. The cryptographic material can, in our case, in case of the vehicle key management system, be platform, product, or even ECU specific. So when I say platform, I mean basically, let's say a car model. A product is, for example, a control unit. ECU specific is the most complex and the most secure thing, which is basically you have keys which are specific to a single ECU. So if you think several dozen ECUs in one single car, and each one has a bunch of specific keys, this gets quite high in numbers in a short time. So for a, let's say, middle-sized tier one, we were doing a vehicle key management system who is doing control units for most of the global acting OEMs. We were talking about several million keys and passwords we needed to create and store. Also, one of the goals of vehicle key management is also good enough randomness. There is a NIST standard defining what good enough randomness is. Actually, randomness is always something I was looking at. Okay, I understand it theoretically, but is it really a huge problem? And there have been successful attacks on a very low level on random number generators in the past. So this is something which should really be taken into consideration when it comes to creating cryptographic material. Then the next goal you want to achieve with a vehicle key management system is to distribute this cryptographic material. It's not really enough to create it and have it in the backend in the data center secure. You need to make it accessible by, let's say, control units or PKI systems in the vehicles. So we have several stakeholders which are interested in or which need to have access to this cryptographic material in specific cases. So, for example, when it comes to development, when we talked about secure boot earlier on, secure boot is basically signing an application file before flashing it, and the bootloader, which also has access to the same key, will then be able to check if the signature is as it would be expected, and only then it trusts the source of this application file. This means basically that you need to make this key accessible in the build stages for the development departments. They need to be able to use the key for the signing of their application files. Then you need to distribute the keys in the control units in manufacturing. This is something which I see very much delegated to the tier ones at the moment, as they are the suppliers of the control units, and they have to be able to store those cryptographic materials in their control units in a secure way. And I will talk later a little bit about the challenges we faced so far when it comes to really make a vehicle key management system work. And one of the worst situations we saw was in the manufacturing lines. They have basically a bunch of high critical requirements, and then cybersecurity comes along and basically wants to wrap everything around them. But more about that later on. Yeah, right. ECUs are mostly manufactured on-premise at the supplier sites, but some of the keys or most of the keys are probably owned by the OEMs. When you talk secure onboard communication, for example, all the control units being manufactured and supplied by different tier ones have to be able to talk to each other. So secure onboard communication is something the OEM has to own and make sure works. So you need to be able to synchronize keys between your suppliers and the OEM. And this is kind of a hard thing to do, but of course it's possible, but you need to do it. Right, and in the final assembly of a car, all the keys distributed must fit together. And this is a complex problem because of the way cars are being produced right now, which is a lot of very smart components are coming from different suppliers worldwide. And in the end, everything has to work as it was intended. And then in the end, you need to store the cryptographic material for certain later on functions, like, for example, the unlocking of a field return or something like that. And this is valid for years to come. So we need to be able to basically have a fully traceable data set of all the keys being ever created and distributed, and in which car and in which control unit, for at least the lifetime of the car. And again, the cryptographic material has to be stored securely on chip. So it doesn't make sense to have a super secure vehicle key management system in the back end, and then you have basically the key stored on chip unprotected in any control unit, directly accessible from the flash memory or something like that. So you also have to have hardware security modules or at least some software supported security mechanisms on chip. When we talk about the back end, which is our main job mostly, then we also talk about additional requirements which come from basically the information technology and the information security domain. So we need to, since we have a key management system in the backend which knows everything, it's a very sensitive target. So we need to be able to protect it against outside hackers and malicious insiders as well, all the time. So we have high requirements for the security of those backend systems. We need to be able to produce 24/7. So this is a business critical application, as it would stop production if it wasn't working well. So availability is a huge issue as well. So besides security, you also need to make sure that you are able to support development, manufacturing, and all the other stakeholders basically all the time, 24/7. And then what we saw is we want to have a high scalability, right? We often start with let's say a single certificate and private key, which is common for a whole car model or something like that. And in this case, you would be able to do this very easily, but then you want to basically do or you need to change some security controls or some claims in a way that it is better, and often you only achieve this with ECU specific keys / passwords or whatever. So this scales up a lot in a short amount of time. So just to give you a number or an idea, for a very common not really a high-end product, we already see, let's say, 5 to 10 different cybersecurity controls in place per ECU or per vehicle network, and most of them need keys. So you would talk about, let's say, 10 or 15 different keys or certificates or passwords per ECU, which is, yeah, it depends on the number of cars you want to manufacture, but it scales up a lot. So the question is, how can we achieve to do this? And when we try to look at the architecture of a system like that, it's very complex. I tried to simplify it a lot, and I did it in a way that I split it up and separated basically 3 tiers or 3 columns. One is the backend and the middleware, which is on the left side, which is basically the stuff you have in the data center. It doesn't really matter if this is the data center of the ECU supplier or if it's the data center of the car manufacturer. You basically need one for each participant in this game. Then you have a bunch of front-end applications, which is basically the ecosystem of your clients, and then of course you have the in-vehicle stuff. So when it comes to the backend, the main component is of course a database. It's shown here as 2 icons, which also gives a hint to the availability stuff. So the database itself, it's the holy grail. It's the place where all the crypto material will be stored after the creation or after the synchronization with all the stakeholders. Normally, I would expect to see hardware security modules being attached to it, which is shown as the 2 HSM nodes down below DB. Hardware security modules are very common, a very common solution in data centers for protecting keys. You probably have a hard time to store all your keys directly in the hardware security modules, as they are normally very limited in memory. So what you probably want to do is have a database and an HSM attached to it via PKCS or KMIP. And that way you are able to achieve FIPS level 3 security. So if you do everything the right way. The key distribution and key management is then taken care of by attached services or applications. You might have interfaces to your suppliers or to your customer, coming from whatever perspective you are right now. So if you're tier 1, you need interfaces to all the different OEMs. If you're an OEM, you need an interface to all the tier 1s. This is kind of complicated for the tier 1s, but we will see that later on as well. So normally you have separated interfaces for internal and external clients. The internal interface is mostly you would expect state-of-the-art REST APIs or typical KMS interfaces like PSCS 11 or KMIP. We also have seen very exotic solutions for interfaces like OpenPGP over email or something like that. You might also see proprietary interfaces with client-side library applications. This is highly specific from instance to instance. Anyway, you want to host those functions in the backend in a way that is secured from the outside, and you want to have very high requirements on authorization and authentication. When it comes to the front end, you basically have a bunch of ecosystems which need to access the key lifecycle management. This is a very simplified view now. You, for example, have the supplier manufacturing, which needs access to your OEM keys, for example. You might have development client-side implementations which need to access certain keys. Since you don't want to export those keys from the backend to protect them from theft or leak, you might want to do it in a way that the function is still hosted in the back end and development can use it. You won't get around exporting keys in manufacturing, though, because you need to provision them to the control units. So basically, every crypto material managed by the vehicle key management system will eventually be distributed into an ECU for the controls we talked about. So for example, secure onboard communication needs, let's say, a symmetric AES key or a certificate or whatever you might be able to achieve to secure your communication. Secure boot is the same thing, IP protection as well. So for all the controls you have in place, you basically need the crypto material on chip. Otherwise, the chip won't be able to do what it is intended to do. In case of secure boot, for example, to check the signature. In case of IP protection, to decrypt the application file from the ROM or the flash before running it. So to protect the crypto material in the vehicle as well, I mean, it's necessary at least for cases where you have the same key being used in a whole fleet or in a whole car model. It is crucial to protect the key in a way that it can't be extracted from the car, or at least can't be extracted from the car easily. Otherwise, you would risk exposing all the other cars to an attack scenario as well. So you might want to have a hardware security module on chip as well. And this is highly specific to the chip, of course, what the chip supports. And one of the most common things is the secure hardware extension, as it was specifically done for the automotive industry. It was drafted up a few years back by the German OEMs, and it's currently part of the AUTOSAR crypto definition. You might have software-based HSMs or even other libraries, stack or hardware provided HSMs or processors, like, let's say, a crypto processor in Xilinx chip or an AUTOSAR crypto stack. So depending on the vehicle key management system implementation, the on-chip software might be in or out of scope for your solution. But in any case, you need to address this as a holistic problem, and this addresses a lot of challenges. Or this is currently a highly challenged field as we see it, at least. So. When it comes to challenges, I want to talk about that in form of different stakeholders. So, as I already told you, manufacturing is somewhat the most crucial thing as we have seen it so far. So we discussed that a secure and reliable key provisioning is necessary here. So for anybody not very who doesn't know how manufacturing looks like, at least in a tier 1 case, but also for OEMs. Manufacturing is basically a highly critical environment. You need to ensure certain cycle times and yields, and you need to do this in a very highly automated fashion. So this is not a good ground for key provisioning itself, because at some point what you will do is you will expose your keys to the software which takes care of the flashing of the key. So let's say somewhere in the line in the control unit, the key gets flashed in the HSM. It might be the flashing station, it might be the end of line station or system test station. It doesn't really matter. At some point, you need to make the key in clear text available to some manufacturing equipment, and this is something which is very critical, because this kind of software or this kind of system wasn't built up with a clear focus on information security or cybersecurity. Of course, their main goal is to ensure that the cycle times are as required, and that the functionality is guaranteed. So now we have the challenge to provide or to make them flash keys in a way that an attacker wouldn't be able to use this weak link in the chain to extract this key from the manufacturing line. So this is something which can only in the long run be solved by taking the chips into consideration. So if you would look at the secure hardware extension, the secure hardware extension does it in a way they call it key memory update. They do it in a way that the new key, which gets stored in a key slot, has to be authenticated with the old value of the slot or with the value of a master ECU key. So this is something which is very sensible to do, because this means if the chip already has a pre-shared secret and we already solved this key distribution problem at this point, we could use that for securing our update mechanism in the manufacturing line. But this would mean we would have chips which are coming from the chip supplier with already pre-established trust, and this is mostly not the case at the moment. So you would probably most of the time you will see secure hardware extension HSMs with basically empty key slots. So the memory update protocol is then nothing more than an obfuscation and can easily be broken. So doing this in a way that this is secure is one of the main challenges, and the same goes for not breaking any of the business critical requirements like high availability and cycle time and yield and stuff like that. When it comes to the distribution of the keys outside of manufacturing, this is mostly a problem between OEM and suppliers. So this is something we can solve with the stuff we already have in place from let's say PKI systems and information security systems. So basically, what we need to do is we need to as we discussed earlier on, we might have, let's say, a secure onboard communication control in place for, let's say, all the control units on the drivetrain field bus. That would mean all the different suppliers would have to, let's make it easy and say all of those control units know one specific key. And this one specific key is being used to sign all the messages on the field bus. This would mean that an attacker coming into the field bus wouldn't be able to participate in the communication as he has no access to the key. We already solved the problem of distributing the key in manufacturing to the control unit, but what about distributing this key between all the different suppliers? So let's say the OEM, as the owner of the secure onboard communication control, would be responsible or is responsible of thinking up this key and supply it to his suppliers in a way that it doesn't leak from there. So normally you would expect a well set up and secure vehicle key management system at all your supplier side, and then you can basically do some key distribution from data center to data center. If that is not the case, you might have the need to make the key accessible for the suppliers and manufacturing without a vehicle key management system, which is kind of hard to do. Or you need to find a way to enable the secure onboard communication with your OEM keys in your manufacturing line. This is also something we have seen so far. This will open up a different vulnerability, which is basically the control units will leave the plant of the supplier unprotected in a way. So whatever you do, you need to make sure that the basic key distribution problem is solved. This is what the left side of this vehicle key management system slide wants to tell you. When it comes to development, we already talked about that. If you have signing and encryption in place, let's say for reverse engineering protection or secure boot or secure software update, you need to make the development workflows able to access this key. And you want to do it in a way that the key itself is not exposed, because you simply shouldn't trust the development stakeholders. And that means you need to take care of a kind of strong authentication authorization system, which allows you to enable this function only for certain clients, and then the clients can make an development integration doing the actual signing or encryption. So talking about very practical stuff, this would, for example, be an REST API where you upload your software and then the software gets signed by the key, or there is a public key which you want to inject or whatever, maybe even encrypt it, and then you can download the file again. That way you can make sure that the actual cryptographic operation, which needs the key, runs in a controlled environment, basically in your backend. I would say this is in scope for a vehicle key management as well. Right. So we already also talked about the hardware support for algorithms, hardware security modules, and file formats. And this is a challenge in itself, because even if there are good cryptographic standards, the very automotive-like chips have very specific solutions in place. And even if there is an AUTOSAR standard defining some basic stuff, you will see very specific ways of how this is handled in the different chips, and even in different versions of the same chip. So in most cases, you will currently only see support for symmetric cryptography, which means you have pre-shared keys, which in itself means, again, that you can't make private-public key combinations work for you. And and you really need to take into consideration how what your chip supports and how you could do this control you're drafting up. This is more complicated from an OEM perspective as well, because the OEM is basically in the need of demanding a senseful level of cybersecurity, which doesn't make all the control units more expensive than needed. So that's also the reason why we see still a lot of symmetric cryptography in place at the moment. I personally would expect to see way more asymmetric cryptography in the future, like the ecliptic curve cryptography, which is as fast as, let's say, AES. But currently, the chips supporting that are a little bit more expensive, which would also push the price for a control unit, which is always something you need to look into. How valuable is your cybersecurity level to you? And in the end, we also have stakeholders in let's say diagnostics, root cause analysis settings for field returns, or let's say you want to run an update which is not going through the predefined channels or something like that. Also, I would say this is also true for the whole testing department. So with enabled cybersecurity on chip, you have a hard time doing your tests as you are used to. So for example, when it comes to RESPA simulation for a single control unit, you simply cannot do it anymore without having the same access to the secure onboard communication keys as the actual car a control unit would be plugged into. And the same goes for debug access protection and stuff like that. So if you're as part of your, let's say, hardware in the loop tests, if you're used to reading out test data from your control unit, then this is probably not working anymore, as you have, let's say, a JTAG lock in place or something like that. So you are also impacting a lot of this stuff. One of the things which gets forgotten a lot is the whole auditability. So at any time in the future, we need to be able to tell who was accessing which crypto material at a certain point, and why he was accessing it and stuff like that. So you also need to be able to not only keep track of all the crypto material, but also of all the different accesses to it. This will make your life in case of a leak easier if you're able to tell where an attack on your vehicle key management system was originating from, or something like that. Yeah, so this concludes a very small overview over vehicle key management systems and how we see it and where they are coming from and the challenges we see so far. We also have a lot of experience when it comes to solving those challenges, of course. Going into detail for those is a little bit too much for this talk today, I think. So if you're interested in real stories or in real solutions, how we can solve those challenges or any other you might see, you can ask me and we set something up. And otherwise, I would like to thank you for your interest and your time. And it was good to have you.
Okay, so at first, thank you very much, Matthias, to bring this topic to us and discuss with us about the vehicle key lifecycle management. We received also some questions. The The first question is related to the HSM. Are you aware about that some automotive companies develop their own HSM chip design, or it's common usage that they use commercial ones, which are also used in other business areas?
So from when we say HSM, there is two different perspectives on this. So you have an HSM in the backend in the data center, and there I would expect to see standard network attached hardware security modules as you can buy them on the market for a long time now. I wouldn't expect some automotive company to develop their own stuff there. When it comes to the on-chip HSM, though, yeah, I would expect to see some specific solutions there as well. I mean, when we started with the cybersecurity stuff a few years back, there was basically nothing there on chip, right? And that's when the OEMs, firstly being impacted by this, drafted up the secure hardware extension as a standard definition with a very small subset of cryptography, which would enable some very basic controls like secure boot and secure onboard communication. So it depends a little bit on what you mean if you are talking on chip or backend.
Mhm. Thanks. The next question, if we extend a bit the scope and look to the backend systems, is there something what you need to take care, what is special for the automotive business to build up or to maintain it, or maybe you have to it somehow? Is there something automotive specific, or is it also in the same way with the same architecture usable for other business areas?
Yeah, that is a very good question. I'm asking that myself a lot. So from a legal point of view, I haven't seen any specific certifications which would be needed. I also don't see the need for them. From a functional point of view, I would say there are quite some differences from let's say a financial application or any other information security application. As this is IoT, as we have products driving around in the field containing a lot of crypto material, we have this distribution problem in a far more complex situation, right? If you are talking about, let's say, HSMs in a classic setup, you can only scope the backend, and that's it. You can basically say, okay, my key distribution problem is somewhat easy to solve. In our case, this is super complex because starting from the OEM, you need to distribute stuff, sensitive stuff, secrets, materials to your suppliers, and then those suppliers need to make those keys accessible from their manufacturing lines. And this means you have like several hundred to 1,000 different stakeholders worldwide, and not one single instance being able to control this. So you can do something like audits from an OEM perspective to make sure that your basic information security requirements are taken care of. But in the end, this is I think the main challenge we have to solve.
Mm-hmm. Okay, thanks. There's another question. Why the keys at production couldn't be generated using a signing request from device to a local registration authority and thus more secure?
Yeah, that is a very good idea. I like it a lot. I mean, I already have seen it from one of the OEMs in the States. They are trying to come up with a solution which uses X509 certificates, where the key is actually never leaving the control unit. And from a strictly security point of view, this is the most secure thing we could do. The answer is quite simple. I haven't seen it except this one instance. So to answer your question, it's possible. It's very much possible. I think it makes it doesn't make the distribution thing easier. So we still need to make sure that the certificate signing requests are handled in the correct way and stuff like that. And the certificates are distributed. But in the end, if you are able to have the key on chip and never leave the HSM on chip, yeah, that is a good idea. Whenever you have support for asymmetric cryptography, that is a good way to do it.
Okay, thanks for that. If we go in the perspective of a supplier which work together with several OEMs, what is your recommendation? How can the supplier efficiently handle the different procedures and backends
Yeah.
with
Yeah,
respect to key distribution and management?
Thank you very much for this question. It's basically what we do. It's our main job. I mean, it's for some reason I don't see any OEM doing the same, having the same procedure in place as the next one. Sometimes we have security hardware extension keys being used from OEM to OEM, but then again, they are quite differently configured and made up, and the whole procedure of switching out those keys from OEM to suppliers is super different. So the answer is you basically want to standardize the processes and the interfaces inside. So to manufacturing, development, diagnostics, and to the OEM interfaces, you basically want to have something in place which is able to manage this. We have, for example, a vehicle key management system which is able to talk to most of the OEM interfaces we have seen so far, and you could reuse it. So my suggestion would be to not do this yourself, but find somebody on the market who is able to do this in an efficient way, meaning reusing solutions and not doing this for one customer.
Okay. So let's come to the final question. Could you share with us one story where you struggle a lot of, or where you had a big challenge to implement the backend system and bring it to work? Only one example.
Mm-hmm.
You mentioned before that you have some experience and also just solved very much problems.
Yeah. So I'm thinking of a good one.
Okay.
So when it comes to the backend system, it's pretty straightforward to do this. It's kind of an IT project. So I would say the backend itself is kind of challenging, but the integration with manufacturing and development is. So I have two, I think. So the first one would be the second most challenging thing for us in our daily job is basically a completely different approach to cybersecurity goals from project to project. So in my opinion, there is only, let's say, a handful or several handful of senseful solutions for the problems we have talked about in the beginning. And you might be able to address those in the same solution or with the same solution from project to project. But then again, we see a lot of very specific and way of doing things. So this makes it kind of hard for us because it's we need to customize and engineer a lot when it comes to development integration and diagnostics and testing integration. The way most challenging part is to make manufacturing work, to be honest. So one of the stories is probably we had a customer where we integrated one of our first keys into or key distribution for an OEM key, an ECU specific key into manufacturing, And in the end, this after SOP of this project, a few months later, it was revealed that they never were able to make it work, even with hands-on support from us. And that meant they basically switched to an offline solution where they extracted one of the keys from the flashing software and reused it over and over again. And that is, yeah, this is the most struggling part for me, because we do a lot to make cybersecurity work, and I mean all of us, right? It's kind of hard job, and we invest a lot of time and a lot of energy and effort to basically prevent cybersecurity attacks, and then it might not be worth anything if one of the links in the chain isn't working as expected. And if that is then again only because some functionality is not working as expected, then it's too bad. So I would say the most challenging part is really the integration of manufacturing. Mostly because of all the different parts in the ecosystem you have. This is an information security hell. You have Windows 7 PCs. You have everybody is allowed to access everything. You have USB slots and stuff like that. And that is the point where we expose our material. So this is something we have to address in the future.
Okay, thanks for sharing these insights with us. And also thank you for the discussion. I would give you the chance to provide some final words to the participants.
Oh yeah, thanks. Some final words. Let's see. So I think vehicle key management, key lifecycle management, it's kind of a complex problem. The good thing is, or the upside is, you can approach it step by step. You don't have to solve everything at the same time. So we can start with, you can start with, let's say, one control or one key or whatever, and take it from there. And every level you adds security. So it's nothing super hard to solve. It's just something you need to do in a very efficient way. So if you want to go into more detail about that, please contact me anytime, and we can talk about that.
Okay.
Thank you very much, and goodbye.
Yep. Also from my side to the participants, thank you for being with us today. I hope you enjoyed this talk. I hope also you are interested in our upcoming talks, and we see us again soon. And then we finish the meeting today. Have a nice evening. Have a nice day wherever you are. Bye-bye.